Okay, so for our research paper presentation, we're presenting our research paper for the digital twin applications in the Internet of Things, and this is a team of Chris Summer and Chase Kosek. So the first question would be the obvious one, which is what is a digital twin? And it's a little bit of just exactly what it sounds like. It's basically a digital version of a physical device itself, and there's a lot of specifics that go with that. And so basically the digital twin as a concept was first introduced in 2003 in a presentation about product lifecycle management by Michael Greaves. And though the term was coined in the early 2000s, the first actual usage of a real digital twin was several years later by the National Aeronautics and Space Administration, or NASA, which everyone knows. And that was where a digital twin was implemented in order to mirror conditions in space for testing and flight preparations for the actual physical hardware of their spaceships, and then it was also used as well with airplanes and the Air Force. So the main reason for the gap in time from conception to execution for the digital twin from that 2003 until NASA actually first used one was the application of the technical requirements for capturing and simulating data, which were not very realistic to achieve in the early 2000s. However, that is no longer the case. So basically, the advancements that made digital twins possible were cloud computing, Internet of Things, big data, better data storage, and the sensor utilization in industrial places. All of these kind of fields advanced very rapidly in the early 2000s to the current day and age, 2020s, um, allowing for the digital twin to become more of a real life achievable goal than a concept at the time like it was. And they pretty much got us there today. So, what is a digital twin still? It's pretty much what it sounds like I said, though NASA defined the digital twin as an integrated multiphysics, multi-scale, probabilistic simulation of an as-built vehicle or system that uses the best physical models, sensor updates, fleet history, and etc. to mirror the life of its corresponding flying twin. That's a really kind of complex description of one, but it's still a good description of a digital twin, and that was the first one that was actually kind of used and first time it was used in this context, so that's a good definition to go by still. But that one is also specific to aviation. So a digital twin is a software model of a physical device which allows for the simulation of different environments, time periods, and variables in a device's lifespan, which also actively accounts for sensor data and operational changes. Um, so some common misconceptions about what a digital twin are or is. It would be the lack of a set definition and the usage of the term digital twin to refer to things apart from the digital twin in an Internet of Things sense, which has led to some confusion amongst people as to what exactly a digital twin is. Commonly, it's confused with two similar models, which are a digital model and a digital shadows, and we'll dive into what those are now. So, a digital model it mainly differs from a digital twin in its lack of automatic data exchange between the physical and digital models. This could have manual data exchange, but it does for sure not have automatic between the models. And for a digital model, physical changes in the real world equivalent have no impact whatsoever on the actual digital version. So like say you have a digital model for a airplane or a spaceship, and the spaceship has some kind of damage taken to the right side of it. This would have no impact on how the digital model perceives the the environment and the capabilities of the actual physical real world counterpart. It would just assume it's still the normal same device that was designed. So some examples of what a digital model are AutoCAD, building schematics, and also device design plans. So just pretty much any kind of schematics for buildings or devices and machines. A digital twin is useful because of it's not only doing the future predictions like a digital model, but it also adapts to real life changes as sensor data is passed back and forth between the twins. So that would be the main difference between the two in this context. So as for the digital shadow, a digital shadow application, the data only flows from one way, not from both. This means that the digital object can successfully receive sensor data and changes in the state of the physical model, but it cannot influence the physical model itself. So an example of this would be using data from a sensor to monitor industrial machines or vehicles, but not changing to simulate their states. So it could pretty much model what's happening, but it wouldn't simulate it. So the main differences here, once again, just summed up in a graph that's pretty easy to understand. It's a two-way flow of data in the digital twin model, and also the interactions between the two, with digital twin mainly being intended to be run in parallel. That's what kind of separates a digital twin from its two other common misconceptions. In a digital model, there can be manual data flow from the physical object to the digital, and in the digital shadow, there's automatic data flow from physical to digital, but there can also be manual in a digital twin. It's from both to each other, and they run together. So, as for the early uses of digital twin, since Michael Greaves first put forth the digital twin model, it's kind of had a slow start, and then the NASA adoption picked up a lot of steam for it. This largely had to do with the technological limitations of the time, as I mentioned before, and some big backings also, however, helped to change this and kind of get some steam rolling on the idea. So one of the first big early adoptions was the NASA and the U.S. Air Force, and the first major was from NASA, highlighting the digital twin model's ability to revolutionize certification, fleet management, and sustainability of air and spacecrafts as the reasons for why they were planning to use it for future endeavors. And the high praise and adoption by two of the U.S.'s most respected in NASA and the Air Force led to a lot of attention being paid to the digital twin. This promised the ability to account for traditional product testing shortcomings and revolutionize machine sustainability, as well as preventative maintenance for machines. And so, what else was an early adoption? That would be Industry 4.0, and this continued the rise in popularity of the digital twin started by NASA and the Air Force in 2013 when Germany proposed Industry 4.0 with the core industrial technology utilizing the digital twin model. That technology was the CPS, or the Cyber Physical System, which consisted of a complex integrated computing, communication, control, network, and physical environment, which basically ends up honestly almost being exactly a digital twin, but the digital twin is just a way to kind of realize what they put together as a goal for Industry 4.0, which was CPS. So the CPS had two main steps, which are right here, and they're the steps for the virtual and physical bidirectional dynamic connection proposed in CPS. So number one is virtual entities such as the design of a product is simulated first and then manufactured. Then number two is the entity virtualization, and that process of manufacturing, using, and running entities reflect their status to the virtual end and conduct monitoring, judgment, analysis, prediction, and optimization through the virtual mode. So these steps are pretty much exactly what a digital twin entails, with the parallelization and the running before and after, and then kind of the exchanging of data, use for prediction and analysis, and all of that. So then, by as early as 2015, GE had also adopted digital twin monitoring and predictive maintenance for their engines, which was another big step forward for the digital twin's life. So as for the importance in IoT, Internet of Things projects are the leading interest in digital twins today in today's economic climate. And digital twins have many applications in today's superconnected world, and Internet of Things sensors go hand in hand with the sensors making digital twins possible. So this can be seen by the estimated market of a digital twin application to exceed a value of 35 billion US dollars by the end of the year 2025. And this estimated market is due to the fact that the digital twins can be highly beneficial to companies with the resources and money to develop that kind of technology for their industry. So further importance in Internet of Things, large tech companies such as Google, Microsoft, and Amazon use digital twin applications to collect and stimulate data from millions of people and devices. And these companies use the high fidelity Internet of Things devices such as cell phones and computers to collect and predict data. And they use the data and analytics to accurately model and predict different systems. This also allows them to guarantee correct behavior for various machine learning systems. So all of the kind of as Amazon Alexa devices, those kinds of things, and the OK Google devices all work in a.
Sorry, I didn't understand.
I don't know if you heard that, but that set off my Google device in my room. But they all work in a way to kind of collect data and act as a digital twin for these companies. And in 2020, it's estimated that there are over 20 billion digital twins being used as sensors, endpoints, or models of some sort. By 2027, it's believed that digital twin will expand beyond its current scope of Internet of Things applications and data analytics. So more importance in IoT, It offers many benefits to Internet of Things and beyond, which the benefits would be optimization of current and future assets, competitive differentiation, and improved user experiences and quality of life. Pretty much just allowing for more data collection, more prediction, more analysis of any sort of device, and also with preventative maintenances and anything like that, it just helps allow the devices to be more effective, efficient, and long lasting. And as digital twin applications gain popularity, they can be combined with AI models, more Internet of Things devices, and other digital twins to form a sort of digital factory. And this would open more possibilities for the uses of digital twins in the Internet of Things in the future. And then down at the bottom here, you can see kind of a mock-up of what a digital factory would entail, which is digital twins, connected AI-enabled equipment, anomaly detection, predictive maintenance, defect and image classification, sustainability and energy and environmental management, 360 view of factory operations, manufacturing as a service, and cloud-enabled factory, and then the process optimization and quality control of the factory. So moving on to technology.
Okay, now we're going to talk about the technology used in digital twin applications. In today's modern manufacturing world, many different applications and systems go through long and complex cycles that consist of multiple phases of creation, production, operations, and disposal. This can be supplemented using digital twin technologies that allow applications to become increasingly more relevant and useful. Digital twin technologies are revolutionizing many of the different fields. These include things such as industry, healthcare, manufacturing, construction, and even more, as you will see later. These are powered by millions of real-time sensors and have real-time updates with years of history of data history. And these models can mirror just about every facet of the production environment or any other types of environments. Over the years, there's been many different digitalizations of certain elements. Early on, there were with the development of the ENIAC and the first computers, it was really just text digitalization, and this didn't really have any application outside of just scientific computing. Further into the 90s with the personal computer, we have the function digitalization, which allows for more job level help and individual workers using computers to do tasks, or even managers with management software. And then with the development of the World Wide Web in the 90s, we see a lot more of business digitalization, with more businesses being able to collaborate and connect to each other and learn their mistakes and learn what works and what does not. And then finally, with new information technologies developed since the early 2000s, we see different things happen on an industry level, and this is made possible by the development of IoT, cloud computing, big data, advancements in AI and CPUs, and also digital twin applications. As can be shown in the chart, the first concept was mainly text, as mentioned. The second was used as a job level manager to aid managers and individual workers complete their tasks. And then the 90s, with the development of the World Wide Web, increased the scope even further, and it allowed individual industries and communities to connect and learn from each other. And then the first enterprise level stuff really started happening around the 2000s, and it lays the framework for digital twin technologies such as IoT and big data and advancements in AI. Like I said, the final step was the emergence of a new generation of information technology. This has allowed for it to encompass entire industries, and there are many things that make this possible, but for digital twins specifically, Internet of Things, everything being able to connect to the internet and talk and send data back and forth is big. Cloud computing is also big. It allows for larger data sizes to be used with more powerful machines. And big data is also another major component of the digital twin technologies. They this allows better models. And finally, the AI and machine learning technologies have advanced so much so that it helps use the big data and these other components to allow for better models. Like I said, these four main advancements in IT form the basis of digital twin applications. There are large scale digital twins would not be possible without IoT. It's simply not feasible for somebody to walk around and collect data from millions and millions of sensors around the country, even. That would be awful for that poor person. Cloud computing allows for better storage and application operation. Like I said, for companies that do not have the ability to use large computers or very powerful computers, doing it in the cloud is a feasible operation and allows for better cost savings and better digital twin applications. Big data collection is a standard practice pretty much in a lot of these digital twin applications. The more data you have, the better your model is going to be, and the longer your data goes back, the better your model is going to be, especially in the digital twin applications. And the AI is another important piece of the digital twin puzzle because it is essentially the brain of the digital twin. It is what does all of the modeling. And here in this figure, you can see that the four main components are the device data, which comes from the IoT sensors, sends up to the AI and the data analytics. The AI does multiple things with that, and it converts it into the best possible model or provides some information for the model. And this is given to the physical model, and it is used for various situations, say updating the model or preventative maintenance. And then also it takes into account the knowledge of the person on the model or the person using the physical device. Now that you have some information on the technologies used in digital twins, we're going to provide some real-world applications. There are many different real-world applications for digital twins, but the ones that we're going to focus on in this presentation will be the digital twins use in vehicles and the automotive industry, NASA and the Air Force's contribution to digital twin and their uses for it, digital twins application in industry and manufacturing, its use in healthcare, its use in IoT and smart buildings, and finally its use in construction and city planning. Like we said before and earlier in the presentation, NASA was the first major adoptance of digital twin for its use on the Apollo programs. The U.S. Air Force and their relationship with NASA also adopted the use of digital twin. Digital twins models revolutionize the ability for different fleet management and sustainability in air and spacecrafts. It's still used to this day for NASA and the U.S. Air Force, and it paved the way for more widespread adoption. In the automotive and vehicle industry, we see that digital twins can be used with connecting vehicles to a digital version. An automotive manufacturer would have the ability to retrieve information from the vehicle and would allow for the examining of performance of the vehicle through their lifetimes. This kind of data collection would help greatly maintain the car's safety, performance, and maintenance. This could also have lasting impacts on the pre-owned car industry, which would help a lot when it comes to seeing what type of vehicle you're buying, if they did regular oil changes, preventative maintenance, or how the car was treated, if it had been any wrecks, kind of similar to other types of pre-owned car registry information you see out there today. In manufacturing and industry, you could see digital twins help manufacturers lead to higher efficiency and accuracy and economic gains in the production. The ability for manufacturers and industrial digital twins to optimize and future aspects of a different system, a different production system, would be big, and it would help increase the competitiveness, productivity, and efficiency of many different manufacturers. In healthcare, creating a digital twin of a hospital operations, capacities, staffing, and care models would help healthcare providers perform better as an organization and increase their quality of care. Accurate digital twin models can help provide great insight on deteriorating conditions and allow for better tailored treatment plans. And companies such as Philips, GE, Siemens, and Toshiba have all started using digital twin applications to help maintain their healthcare systems and their machines. Digital twins are heavily reliant on the real-time monitoring and data collection capabilities of IoT devices. The data gathered from these IoT components is essential in order to help monitor and create an accurate, and actual digital twin. The inverse flow of information is also true. You need to be able to receive information. If you're an IoT device, you need to be able to talk to the digital twin and make updates. This is mostly done through APIs in current IoT devices. There are a number of different challenges when it comes to using IoT devices, and these are due to a multitude of different things, but most commonly it's the lack of standardization between different IoT devices, the lack of high fidelity two-way connections for the accurate and timely flow of information, and individual device security is another major component when it comes to IoT devices. Finally, in construction and city planning, there is a little misconception that the 3D models used in construction are digital twins, which they're not exactly digital twins. These individual models, called building information models, or BIMs for short, are not exactly digital twins because they lack a connection between the physical and digital model. A BIM is typically used to test and solve issues with a building before it is actually built. But, that being said, digital twins do normally consist of many components of a BIM, or even sometimes use the entire BIM paired with a multitude of different sensor arrays. In city planning, however, the digital twins are far more useful for many parts of the city. These parts of the city include buildings and developments, maintaining and building new roads, the logistics of getting your Amazon package to your house, managing different traffic traffics or keeping, say keeping the red light green for long enough for a large amount of traffic to not back up the entire city. Your different public services, such as your fire departments and your ambulance networks, your power grids, and monitoring your people in your city, because knowing how your city is going to grow is crucial when it comes to city planning. Being able to monitor all of these components is key in being able to improve the quality of life for the people in the city.
Okay, so moving on to the conclusion. So in conclusion, the digital twin has gained a lot of attention over the last decade, and there are many advantages of having a virtual clone with the ability to predict, monitor, share data, and control the physical twin, with some of those being more efficient machines, easier maintainability, and real-time monitoring. And these benefits, however, are not without challenges. Some of those challenges include big data handling, device connectivity, real-time synchronization, simulation software, development and maintaining, as well as updating, as well as cybersecurity concerns, especially with kind of sensitive data, such as like a nuclear reactor might be if you had a digital twin of one of those. So there are also the limitations of cost, complexity, and research. And the cost to develop, test, and implement a digital twin are still very high and are much too high for some industries or some companies to take on. And there are long-term rewards of health and efficiency, though that can also make the cost well worth it, as they would eventually regain the costs that it would have took to achieve a digital twin. And despite all these challenges and limitations mentioned, the digital twin is still remains a promising young Internet of Things technology today. So we hope you all learned something about the digital twin, and we hope you all enjoyed our presentation. Thank you.